Between the glittering nodes of galaxies lies an invisible network strands of dark matter weaving through the cosmos in vast filaments. Though we cannot see it with our eyes, its presence reveals itself in the motion of stars and the bending of light, forming the cosmic web that underpins all large-scale structure. Imagine drifting along one of these filaments, a river of unseen mass flowing through the universe. At first, the filament appears empty. The darkness between clusters is profound, but gravity is at work. Dark matter particles, whatever they may be, are drawn together by their mutual pull, forming elongated overdensities, tens of millions of light-years long but only a few million wide. Gas hydrogen and helium from the primordial universe feels this tug. It drifts into the same channels, cooling and condensing under pressure, seeding the filament with diffuse plasma that glows faintly in X-rays. Here and there, small galaxies emerged dwarfs that formed early and have since been shepherded along the dark river, their orbits following the filament's spine. As the filament guides them toward the gravitational wells of massive clusters at its ends, these dwarf galaxies are stripped of gas and stars by tidal forces, their debris streaming behind them like cosmic breadcrumbs. Meanwhile, larger galaxies, growing through mergers and accretion, are drawn more slowly, spiraling inward along these dark corridors. Flowing silently beside the luminous matter, the dark matter river deepens. Its density rises, creating a stronger gravitational current. Gas accelerates along the filament, shock heating as it collides with other streams. In some regions, the gas cools rapidly, fragmenting into cold knots that collapse into galaxies in their own right, bright islands of stars, linked by the faint riverbed of hot plasma. Over billions of years, these filaments feed the universe's largest gatherings. At their intersections, where multiple dark matter streams converge, galaxy clusters form, amassing hundreds or thousands of galaxies in a gravitational node. Within these clusters, dark matter still dominates. Lensing maps show it enveloping the luminous galaxies in halos that guide their motions. Without the rivers of dark matter, clusters would not emerge. Without their currents, galaxies would not find the paths to collide and merge. The ripples in the cosmic microwave background, the subtle anisotropies imprinted at recombination, foretold these structures. Today, telescopes both on Earth and in space through galaxy surveys and weak lensing measurements trace the invisible scaffolding, converting starlight and distorted background galaxies into maps of dark matter's flow. We see the rivers carved by gravity. We hear their echoes in redshift space distortions, and we feel their pull in the motions of galaxy pairs. And yet the true nature of dark matter remains a mystery. Is it made of weakly interacting massive particles, sterile neutrinos, or something more exotic? Laboratory experiments and astronomical observations race to detect its particles or reveal its interactions. Meanwhile, we continue to map its rivers, charting the cosmic web's evolving architecture. In doing so, we learn not just about galaxies and clusters, but about the hidden substance that embraces the universe dark matter's invisible, embrace guiding gas and galaxies along its ancient, river-like filaments from the primordial past into the cosmic future. In a distant stellar nursery, a massive star initially tens of times the mass of our Sunhas shed its hydrogen envelope, revealing its blazing wolf, riot core. This stripped star is hotter than 80,000 Kelvin, its surface a furious landscape of radiation and particle flux. Here, the stellar wind is no gentle breeze. It is a gale so fierce that the star loses mass at a rate 1,000,000 times higher than our sun, ejecting material into space at velocities exceeding 2,000 kilometers per second. From the star's photosphere, photons steam outward, transferring momentum to ions in the outer layers. These ions, carbon, nitrogen, oxygen, and heavier elements forged in the star's core, driven off as a continuous outflow. The wind is dense and clumped, a turbulent spray of helium and metal-rich gas. In UV light, we see P Cygni profiles broad emission lines with blue-shifted absorption trough signatures of the superheated wind streaming away at breakneck speed. As the wolf, riot wind collides with slower material ejected during earlier red supergiant phases, shock fronts form. These shocks heat the gas to millions of degrees, emitting X-rays that can be detected by space observatories. The shocked zones are luminous, intricate structures, filaments of hot gas and cooler, denser clumps where the winds collide, compressing and cooling the material into knots that may seed future star formation. Over tens of thousands of years, The Wolf Rayet phase carves a cavity in the surrounding interstellar medium. A wind bubble expands, its dense shell traced in radio and infrared as heated dust glows. Within this shell, enriched gas-heavy elements like carbon, nitrogen, oxygen, and neon mixes with the ambient medium, seeding it with the ingredients necessary for rocky planets and, eventually, life. But the star's life remains brief. Within another 100,000 years, core temperatures will reach the threshold for advanced fusion, producing iron. No further energy can be extracted from iron fusion, and the core will collapse in a fraction of a second. The Wolf Rayet Windwance, a torrent of enriched gas, will cease as the star explodes as a type Ib or Ik supernova. When that explosion occurs, the wind-carved cavity will shape the remnant's expansion, producing asymmetric debris fields and complex shock interactions. The heavy elements carried by the wind will be swept up in the supernova blast, traveling farther into the galaxy, seeding new molecular clouds with iron peak and alpha elements critical for the next generation of stars and planets. Astronomers study Wolf Rayet winds by observing their spectra, mapping their radio emission, and modeling their dynamics. Yet many questions remain. How clumped is the wind? What drives its instabilities? How do magnetic fields influence the outflow? Answering these questions not only illuminates the life cycles of the most massive stars, but also clarifies the chemical evolution of galaxies. In the end, the Wolf Rayet star's superheated wind is both a goodbye and a promise, a farewell of intense mass loss before a cataclysmic death, and a promise of cosmic renewal as its heavy elements swirl into the interstellar medium. It is the voice of a dying giant, blowing through space at thousands of kilometers per second, seeding the galaxy with the metals that build worlds, oceans, and perhaps, one day, thinking beings who gaze back at the stars.